Let's do problem 55 on page 329 in chapter 10. And let's read the problem first. It's right here. It says, we have a metal can containing condensed mushroom soup and has a mass of 215 grams, a height of 10.8 centimeters, a diameter of 6.38 centimeters. It is placed at rest on its side at the top of a 3-meter long incline that is at 25 degrees to the horizontal, and then it is released to roll straight down. Assuming mechanical energy is conserved, calculate the moment of inertia of the can if it takes 1.5 seconds to reach the bottom of the incline. Which piece of data, if anything, are unnecessary for calculating the solution? So there we go. Let me, so I kind of set it up here. And so the can, well, it starts from rest, so V naught equals 0. And it rolls down at 1.50 seconds. And this is at 25 degrees, 3 meters long, and so on. And we want to know what is the rotational inertia of this. Well, and one of the hints is that it took, mechanical energy is conserved. That is, the mechanical energy here, E initial, is equal to E final, which is down here. Okay. So, let's see what we can do. Let's start off with energy, since they kind of told us that explicitly. E initial equals E final. Well, what kind of energy does it have initially? It's at rest, right? So there's no kinetic energy, right? So what does it have? Well, it has height, right? It has gravitational potential energy. So we're going to call that mgh for height. Now, that's not the height that's up here, right? That's just the length of this can right here. But that's this, you know what? I'll call this capital H. And then, now it doesn't, at the bottom, it's not going to have any gravitational potential energy anymore. But what kind of, where's all the energy going to go? It's going to have kinetic energy, right? And it's going to be rolling, right? So it's going to be 1/2 I omega squared. Now this is promising because we're trying to find the rotational inertia. And this has rotational inertia in it. So if I can get all this other stuff, I can solve for I. So this kind of tells me what to do. Well, I know what M is, and I know what G is. Let's solve for H so I can get this part. So H, if I look up here, well, notice that the hypotenuse is 3 meters, and I want to know the height, and this is 25 degrees. So I know that the sine of 25 degrees is equal to the height over the hypotenuse, which is 3 meters. So H equals 3 meters times the sine of 25 degrees. And so I'm going to get my calculator out. 3 times the sine of 25 degrees. And that's 1.268 meters. Well, and now I can solve for E initial. And usually I like to leave things in variables, but this is kind of a big, long expression. So I'm going to kind of condense it down to numbers. What is MGH? MGH now. Well, that's equal to 215 grams, or 0.215 kilograms, right? We want to get this in joules, so we have to use kilograms, times 9.8 newtons per kilogram, times H, which is 1.268 meters. So this is my mechanical energy for this system. 0.215 times 9.8 times 1.268 equals, so we have 2.672 joules. So this is the amount of energy that's in this system. Okay. Well, now let's work on this guy right here. Do I know the mass? Yes. Do I know what the final velocity is? Well, it's not given, but if you think about it, this is going to roll down with constant acceleration. So, because it's flat, so I can use the kinematic equations. With this time, I know what the initial velocity is. I want to find the final velocity. Now I know the time. Now I don't know what the acceleration is, and I don't need to find it. So I look on my list of kinematic equations and I say, okay, what doesn't have acceleration in it? And it's the second one. Delta x equals v naught plus v over 2 times time. So v, now this v naught is 0. So v is going to be equal to 2 over delta x divided by time. Okay, so what is, that's 2, and delta x, well, it goes down 3 meters, right? And if I go off screen, let me know, okay. 3 meters divided by time, well, it's given to be 1.50 seconds. And so now I can say, well, that's 6 divided by 1.5. Wasn't that 4? Right? So that's 4, no need for a calculator, 4 meters per second. So now I got that. Now what is omega? I need omega. How would I get omega from this? Yes. And it's rolling motion. The can is rolling down the hill. Now, if it's rolling motion, what do you know about the relationship between the velocity of the can, the linear velocity of the can? Yep, V equals R omega. That's right. So the velocity of the can is equal to R omega of the can. Well, so omega is equal to V over R. Well, that's 4 meters per second divided by, now what's the radius? Well, it's the diameter divided by 2, right? But you have to make it meters. So I'm just going to use a calculator so I don't make any stupid mistakes here. It's the diameter is 6.38. Divided by 2 equals, so that's, and then divide that by 100. So you get 0.0319 meters. Now, here's what I like to do. The radius, that's how many meters you go if you rotate through a radian of rotation. So it's like meters per radian. So the meters cancels the meters. You reciprocate and multiply, you get radians per second, which is omega. So 4 divided by 0.0319, I'm getting 125.4 radians per second. That seems really high to me, but the radius is tiny, and it's moving fast, and the radius is only 3 centimeters, so that's like that, and it's going 4 meters per second. Did I do that right? Well, that's a long ramp, 3-meter ramp. So yeah, I think all the numbers look good so far. And notice that I check my work. I really check to see, does that look reasonable? Is that, when you just have to kind of try to do that. Well, now I've got omega. So, and I have all of this. So now I just have to solve for I. So I is going to be equal to that mgh that I solved for already, minus 1/2 mv squared, and I'm going to divide it by 1/2 omega squared. Oops, I'm off screen. Let me zoom out a little bit. Well, this mgh, I already figured that out. That's 2.672 joules equals, minus 1/2 the mass, 0.215 kilograms, times the velocity squared. That's 4 meters per second squared. And I'm going to divide all that by 1/2 of the angular velocity squared, 125.4 radians per second squared. Yikes. So I'm going to just do these separately and write them down. So 0.5 times 0.215 times 16 equals, so I get 1.72 joules up here. Now this number is going to be big, 0.5 times 125.4 squared, and I get a big number. This is 7,862 radians per second squared. Well, just per second squared, actually. So let's solve for I now, the final answer. So we have this 2.672. That's the energy that we started with, minus the energy that's in the linear kinetic energy, which is 1.72 joules equals 0.952. And then to find I, we have to divide by 1/2 omega squared, which we got. So I'm going to divide that by 7,862. And that's going to give me an I that's very small, but it's a soup can. We would expect, if you're going to do this in kilograms and meters squared, I mean, think about it. This is a little can. So it's got very little mass, and its mass is not very far from the axis of rotation in terms of meters. So it makes sense that the kilogram meter squared is going to be really, really a small number. And you get 1.21 times 10 to the negative 1, 2, 3, 4. Kilogram meter squared. That should be my answer. Now, let's check the units here. This is joules on the top. Well, what is joule? A joule is a kilogram meter squared per second squared. And then over on here we have 1/second squared. Radians is a dimensionless unit. Remember, it's a meter per meter. You know, when you do a radian, it's arc length divided by the radius, so that's a meter per meter, so it's dimensionless. So that does indeed have to give a kilogram meter squared. So I think that's my answer. Let's zoom out so we can see the whole problem now. Now I'm going to look it up.
That's right.
Is that right?
Yep.
Woot! So I looked it up in the back of the book. Well, Jacob did. So he put a big star next to it. So let's review the whole thing. What's the big picture here? Okay? The big picture is this. They kind of gave you a hint. They said, assume that no mechanical energy is lost. When they tell you that, that's awesome. If no mechanical energy is lost, that gives you an equation. E initial equals E final, right? The initial mechanical energy equals the final mechanical energy. Yay! Okay, and then you have to say, okay, where is all the energy initially? Oh, well, then you have to think. You got to be a physicist. Where is that energy? Well, it's not moving. It has no kinetic energy, but it has been lifted up in a gravity field, so it has gravitational potential energy, mgh. Oh, wait a minute, but what is h? Oh, they gave me this, they gave me the angle, I can figure out what h is. And you plug, and so now I can figure out how much mechanical energy I started. Then you say, well, where is the energy at the end? Well, all its gravitational potential energy is gone. It's all gone into kinetic energy, but then you have to know, this is when you have to know what you're doing, it's rolling motion. When something is rolling, it has both linear kinetic energy, because it's translating, plus it's spinning. Okay, and that what's nice about this equation is what we're trying to find is in the equation. So now that kind of tells me what to do next. Well, this tells me what to do. Well, I got to figure out h, which I did here. I have to figure out the velocity. Okay. Oh, well, they gave me 3 meters and 1.5, and it's a flat, I can use kinematics to do that. So you have to remember your kinematics. That's what makes this a hard problem. And you have to know, because it's rolling motion, if I can find the speed, I can find the angular speed. If I know the angular velocity, or the linear velocity, I can find the angular velocity, because they're related. And that lets me find out. And then it's just, now I know everything. It's just a matter of not screwing up the algebra. Okay? Make sense? Any questions? Wow, 18 minutes. That is all.